more clumpy morphology, a larger effective radius, and a weak nitrogen fluor emissions compared to the compact galaxies. And very recently, NASA published their work on the MOM Z14, which is the galaxy that has the highest redshift up to date, and with the spectroscopy confirmation. And this galaxy also falls into the compact galaxy with a very strong nitrogen emission and smaller galaxy size. And however, although they found they found a more continuous distribution of the galaxy sizes by including more galaxy samples when by adopting a larger magnitude range, and also including those only have photometric redshift, and also doing the stack for those same galaxies. And they found a more continuous distribution. In fact, this is a log-normal distribution. They can fit by a log-normal distribution with the median at 130 parsec, and the standard deviation is comparable to the local galaxies. So by combining with the low Thursday index, they concluded with a disk formation scenario that acquires at least half of the specific angular momentum from the host halo at such redshift. Theoretically, it's not hard to explain the compact galaxies at cosmic dawn, either by the compact star formation, like the feedback-free starburst scenario, which predict most of the star formation occurs in the clumps, which have a size around 30 parsec at the redshift 9 or so, and even smaller at high redshift. Or you can use AGN activities to explain when the AGN outshines the stars. For the extended galaxies, and because of their clumpy structure, it seems like there are mergers going on at such redshifts. And indeed, cosmological simulations have shown that the merger rate is higher at higher redshift. And here on the left, it shows the constant merger rate given the fixed redshift being. And because of the cosmological factor spans a shorter time at fixed V with the redshift increases. So it means you have more halo mergers at higher redshift, which can possibly explain the extended morphology, the clumpy morphology. But they are not necessarily correlated. Like the larger effective radius does not necessarily mean that they're clumpy. So we try to understand the physics behind them. We use the zooming cosmological simulation of Ramses, and we zooming the massive halo, which is around 10 to 11 at the redshift 9, and the subgrid models is the turbulence model and the multi-free fall star formation model, similar to what Dean mentioned yesterday. And by using this multi-free fall star formation model, allows us to have a physically driven star formation efficiency, which here you can see depends on the Mach number and the virial parameter. And our resolution, we have the resolution of 2 times 10 to the 4 solar mass for the dark matter, and for the cell size is around 10 parsec during during all the simulation time. So here shows a movie, and on the top you see the star formation rate, and at the bottom you see the dark matter surface density, the column density of the gas, and the stellar surface density. So there's the first stars formed at around redshift 16, and because of the collapse of the gas under the potential of the dark matter halo. And then at redshift 14 also you will see there's major merger happens and create a very complex galaxy at around redshift 12. And then after that there's a sequence of minor mergers, or like there's a lot of satellites orbiting around the central galaxy, and the galaxy size grows, and also the morphology becomes clumpier and clumpier. And I also create the UV mock image to directly compare it to the Japanese observation. But unfortunately here I don't have very high time resolution, but still you can see that from redshift 14 to redshift 9, the galaxy becomes clumpier and clumpier and also larger and larger. So it means, so on the left you can see that the redshift 12 is a very compact galaxy, and on the right it becomes clumpy and extended, which means in the same simulation I have two types of morphologies, but at different time and stellar mass. So for the compact galaxy, for the compact morphology at redshift 12, the stellar mass is around 10 to 8, and halo mass around 10 to 10, and gas mass is higher than the halo mass, than the stellar mass. And for the effective radius, you can see that it's quite compact, around 30 or 40 parsec. But on the right, at the redshift 9, the halo mass becomes 10 to 11, and the stellar mass becomes 10 to 9, and the effective radius becomes like 100 to 200 parsec. And if you directly compare it to the observations, here I very broadly had two things. One is a minus 22 to minus 20, and one is a minus 20 to minus 18. So in all cases, our simulation seemed to fall in the ballpark of the observations, which also below this is favored to the compact morphology, but our galaxy actually is brighter than minus 22. So at the end of the simulation, it reached to the bottom envelope of the size evolution. And here I'm showing the size magnitude relation, and the simulation is color-coded by the redshift. And still you can see that the other observations are shown by the dots, and our simulation are in the ballpark of the observations. So then we're trying to understand how to make these galaxies clumpier and extended. So first we want to understand if those new stars or the new stars are from the mergers from of the stars from the outside, or is from the stars inside. So we try to look at in situ star formation, and this is calculated by focusing on the galaxy at the redshift 9 and trace back their birthplace, and to find if the distance to the center is within the 15% of the real radius or not. If they're in it, then it's in situ formation. And we found that within 1 kiloparsec, or in terms of the effective radius, the 5 effective radius, over 90% of the stars are in situ formation. And if you look at their birthplace, then the birthplace throughout from redshift 9 to redshift 14, the birthplace of these new stars are around 100 to 200 parsec. And when you compare shown by the orange line, when you compare to the blue line, which is their current place, you see that there's actually a minor contraction because of everything goes inside. And here shows the radial kinematics of the stars and gas. And here I'm showing the three component stars, gas, the in situ stars, active stars, and the gas. And inside 700 parsec, most of the mass is composed by the stars, and the outside is by the gas. And for the inflows, we found the inflow fraction is higher than the 50% for the in situ star, which means that after the stars are formed, they are migrating inward. And we found that we have a fictive form at redshift 9. Here I'm showing the face-on view of the galaxy and edge-on view of the galaxy. This is a stellar surface density, and here I'm showing the V phi, the rotation velocity. And you can fit the density profile by exponential disk profile with the scale radius of 200 parsec. And if you measure the HLR of the stereo disk, it's around 0.25. So it's quite a steady disk. The time evolution of the zero sigma suggests that it continues growing with time from the spheroids to the disks. And at the end of at the redshift 9, the zero sigma is comparable. And also, with increasing of zero sigma, the effective radius also increases and the stellar mass increases, which means these three properties are correlated to each other. So at the end, I want to show the efficient star formation that the star formation are mostly in clumps. So here I'm showing the epsilon FF, which is the star formation efficiency. And for the red, it means a high star formation efficiency. For the yellow, it's high star formation efficiency, and blue is low efficiency. And you see that you can see the orbits. That's because of the star forming clumps are orbiting around the galaxies. And those yellow ones suggest a very high efficiency, and I can plot the profile for this, and the efficiency peaks around 500 parsec, and this traces back to the density, the different density property, temperatures, and those light dispersion or something. And if you plot the time evolution of the star formation efficiency, you see that the blue line, which is the global efficiency, goes up with time, and the orange line shows the local efficiency, and the green line shows 1 over is outflow. If it's a self-regulation, then what is efficiency looks like, and all three properties correlate each other. Okay, so this is a summary. I just want to introduce this extended clumping morphology might be because of the minor mergers, and the stars are mostly in situ in the outskirts of the galaxy, and it forms a disk at the redshift 9, and there's a very efficient star formation in the clumps of the disk, and this efficiency grows with time. Thank you.
Thank you. We have time for one question, probably. Yes, though I don't see the next person anymore.
Yeah, this is very interesting. I was wondering, what's exactly the role of the merger? Is it just to move gas to the outskirts where it can form stars, so it's driving higher Mach number and making efficiency higher? So can we look into that?
That's a very interesting question. So by looking at the star formation efficiency, and we can see that the density is higher at like 500 or 600 parsec, and the Mach number is also there's a peak around there, which might suggest that the minor mergers there's interaction between those satellites and the disk.
Okay, let's thank our speaker one more time.
Thank you.